First time I saw a cubical quad antenna was decades back on the rooftop of a VU Hamfront. It was a two-element cubical quad for 20-meter amateur radio band. As he did not have an antenna rotator, he used to rotate it manually, which he called as Armstrong method. Yesterday, another VU Hamfront has installed a multi-element cubical quad for 2 meter as part of his satellite tracking system for working amateur radio satellites. Now I expect him to be heard on LEO satellites with a booming signal. Cubical quad antenna can be considered as the equivalent of two bent dipole antennas stacked one on top of another with a single feed line. Hence, they have a gain of about 2 dB over a simple half-wave dipole antenna. Each limb of the cubical quad is quarter wavelength, so that total length of the loop is one full wavelength. In case of HF antennas, cubical quad antennas can be constructed over an X-shaped frame with wires running around the perimeter of the square formed by the X frame as diagonals. Multi-band cubical quads can be made with lowest band element at the perimeter and inner band elements within them at a distance towards the central point of the X frame. This can be considered somewhat similar to the arrangement of elements in a multi-band hex beam antenna. VHF-UHF cubical quad antennas can use frames supporting tubular elements as well. Small size will permit use of such elements without unduly increasing the weight of the antenna. Frame of a cubical quad antenna should be strong enough to resist the force of wind, which is more likely to affect the cubical quad than a Yagi antenna. This could be the reason why it is not as popular as Yagi antenna, even though it has a gain of 2 dB over a Yagi of similar length. For a half-wave dipole antenna, the point of maximum current is at the feed point and point of maximum RF voltage is at the ends. As a cubical quad can be considered like a couple of stacked dipoles which are bent at right angles in opposite directions. The current maximum is at the feed point and at the point opposite to it. Voltage maxima will be at 1/4 wavelength from the feed point. When the frame is kept like an X, the cubical quad will have a square shape. If it is kept like a plus, the shape of the cubical quad can be considered to be diamond shaped, there being 45-degree tilt in the frame between these two orientations. Both these formats in the usual type of mounting give horizontally polarized signals. If the antenna is rotated 90 degrees, it can radiate vertically polarized signals as in case of Yagi antennas. As with the Yagi antenna, cubical quad elements can be arranged on a boom with one reflector behind the driven element and a series of directors in front to create a beam antenna. A reflector behind the driven element, which is slightly longer than the electrical full wavelength by 3 to 5%, will make it inductive and resonate below the nominal frequency of the driven element. Another way is to use the same length reflector element and add a small short circuit stub, offering some mechanical advantages for the quad beam antenna. Directors should be either shorter length or an open circuit stub so that resonance is above the nominal frequency and be capacitive. Adding more directors will increase gain in a decremental way. 0.15 to 0.2 wavelength spacing between the elements will give a feed point impedance around 50 ohms. While reflector gives a gain of around 5 dB, first director gives an additional gain of 2 dB. More directors increase gain by 1 dB each. 4 or 5 directors will be optimum in view of diminishing returns with large number of directors.